Okay, so let's get started here. So last time we started talking about these transforms, and we could try to figure out these like a UV substitution for two integrals. So perhaps we had some area integral over a region R of f of x and y, but this was a complicated integral, and we had some kind of substitution that we could do for x and y in terms of u and v. So what we do is we transform the region R over to UV space, and it becomes some region S. Our integrand just becomes f of x and y with u and v substituted in. Then we have this transformation like quantity here, this Jacobian. We have the absolute value of the Jacobian. And then we have the dA in the UV space. So this is du, dv, in no particular order. So we could do either depending on what the region S looks like. So today we're going to be primarily dealing with examples. So let's go ahead and dive in. Our first example is going to be evaluate the integral from 0 to 4 y over 2 to y over 2 plus 1 2x minus y over 2 dx dy by applying u is equal to 2x minus y over 2 and v is equal to y over 2. So the first thing to do is we're going to sketch out the region in xy space. So let's go ahead, plot this region at x and y. So I look at my bounds here. I know I go from the line y equals 2 up to the line y equals 2 plus 1. So this looks like this. We can rewrite in case it's a little unfamiliar. We can say that this is, x is equal to y over 2, or this is y is equal to 2x if you're more comfortable with that. Or we could say that this is x is equal to y over 2 plus 1, or this is, we multiply by 2 everywhere, and then we move over this, what becomes a 2, and this is y is equal to 2x minus 2. Okay, so this looks like the line y is equal to 2x, and then a little bit of translation of that line over like this. And then the top of it. And this is the region in the xy plane. So this is our R, right? And then we have down here the edge y equals 0. We have here y is equal to 2x minus 2. Over here, we have y is equal to 2x. And at the top, we have y is equal to 4. These are all very important. We need to know the edges of the region. So we're going to write down the relation of all 4 of these boundaries. So now we have to convert what this object looks like in the UV space. And I'm gonna say this, and this is very important. The most common mistake that I see is they take these equations in the bounds and they directly substitute in the definitions for the substitution and assume that that's the new bounds. That's incorrect. What we need to do is redraw this thing into the UV space and then figure out what the bounds are from there. So please, please, please do not just substitute in the transform into these bounds. So let's look at all of the edges and see what happens when we plug in the transformation into the edges. So on y is equal to 2x, we go ahead and plug in a relationship. So if we look at u and v, right? If y is equal to 2, if y is equal to 2x, you'll notice here that this numerator is 0, right? So if I go ahead and plug that in, I get that u is equal to 0. And if I plug y equals 2x into my v expression here, I get that v is equal to x. Okay? Well, x, notice, on this interval, it runs from 0 to 2. So here is when x is equal to 2, right? Because that's when y equals 2x becomes 4. So we'll just put a little mark there, 0 to 2. And we're going to do this, this procedure a few different ways, and you can do whatever feels more comfortable. On this next segment, what we're going to do is on the segment y equals 0, I'm going to plug in y equals 0 into my uv expressions. So if I plug it into u, I get that u is equal to x. And on this segment, y equals 0, I go from 0 to x equals 1. So this goes from 0 to 1. We'll just keep track of that there. V, on the other hand, when I plug in y equals 0, is just 0. On y equals 4, the upper part of this like slanted rectangle, we get that u is equal to x minus 2. Well, on this interval, x is 1 out 2. Sorry, it's actually, no, it's 2 out 2, this point here, which ends up being x is equal to 4. Right? So on this interval, x ranges from 2 to 4. So that makes this whole thing ranging between 0 and 2, right? Because we're just subtracting 2. So now v becomes equal to 2. Oh, we have a chat. How are we finding the ranges? It's the range on that segment. So for instance, the very first one we did, y is equal to 2x, we had this x here. Well, x on that segment alone goes from 0 to 2. So that's why we just kept a little sidetrack there. Okay. So now on the segment y is equal to 2x minus 2. If I plug that into my u expression, I just get 1. And if I plug this into my v expression, I get x minus 1. So on this segment, notice that x ranges from, we're going from x equals 1 out to x equals 4. So we go no, it can't be right. Oh, no, this is, whoops. This thing here should hit, no, at x equals 1. Yeah, it's 0 here. So on this segment, we go from 1 and we go all the way up to when this is 4, or we need x to be 3, right? So on that range, we're subtracting 1, so we go from 0 to 2. Okay, so now let's plot what this thing looks like given these guidelines. Here we go. So this is u and v. So these each kind of make up a new bound. So let's take a look at the first one. This is u equals 0. Okay. Maybe you don't necessarily have to worry too much about these ranges because we're going to see here that we're going from u equals 0. So if u is equals 0, this is just the v axis. So it's all of this, right? And then we'll worry about the ranges in a second. This one here, I have that v is equal to 0, or all of this right here. From here, I have that v is equal to 2, so maybe something like up here. And then here I have that u is equal to 1, or all of this. So you can imagine that we're actually going to fill in this box right here. So this is actually going to be our new region. This is S. The ranges help because we can talk about the range on that line segment. So V ranges between 0 and 2 on that interval. And our V equals 0 here ranges from 0 to 1. It has a width of 1. And this had a height of 2. So that's how those bounds kind of come in. If you're a little bit confused about the bounds, we're going to do alternative ways of transforming from xy to uv. Can we repeat why the last bound is 0 to 2? This should be because x on this interval, which is this guy here, ranges from 1, x equals 1 to x equals 3. And we're subtracting 1 from it. So we go from 0 to 2. Okay, so this is now our S domain. And this is just a simple rectangle. So we should be able to quickly find the bounds for this in UV space. But we're not done yet. Before we set up our integral, we also have to find the Jacobian. So the Jacobian of UV is partial x, partial u, partial x, partial v, partial y, partial u, and partial y, partial v. Okay, so we need to find x in terms of u and v. We don't have that just yet. We have u in terms of x and y, so we're going to go ahead and find those. So first off, v equaling y over 2 is easy to solve. We get that y is equal to 2 times v. We know that u is equal to 2x minus y, so we'll go ahead and plug in 2v over 2. So now we can just solve for x here. This is x is equal to u plus v. Perfect. So now let's look at this determinant. This is when we do partial x, partial u, this just gives us 1. Then partial x, partial v gives us 1. Then partial y, partial u gives us 0. And then partial y, partial v is 2. So we can take this determinant and we get just 2. We take the absolute value of that for our integral. So that's just going to end up being 2. So we can rewrite our xy integral now. So 0 to 4, and then y over 2 to y over 2 plus 1 of 2x minus y over 2 dx dy. So now this is where we look at the bounds for the region S, right? So perhaps we have to talk about what integration order we're doing first. I'm actually going to fill out this and then come back to the bounds. So if we look at our substitution, we actually realize that this was just u. We have the absolute value of our Jacobian, which was just 2. So we'll put a 2 here. And because this is a rectangle, it's really easy to do either order. So we're going to just do du dv, right? And u goes from 0 to 1, and v goes from 0 to 2. So this messy double integral, when we do our substitution, is just this rectangle of 2u. That's pretty easy. So let's go ahead and integrate this. This is 0 to 2 of u squared, u equals 0, and u equals 1 dv, or just 0 to 2 dv, which is simply equal to 2. Okay, so let's do another example where we do a little bit an alternative of finding the region S. So this time, we're going to evaluate, example. We're going to evaluate the double integral from 0 to 1 and 0 to 1 minus x, the square root of x plus y times y minus 2x squared dy dx. With x being x plus y and v being y minus 2x. So this time what I'm going to do is I'm going to first find x and y in terms of u and v. So let's solve for this. I can look at this expression here, and I say that y is equal to u minus x. Okay, it's not quite solving for u and v just yet. We have this x in here, but what I can do is plug this back in to our second expression, so that I have v is equal to u minus x minus 2x. This is equal to u minus 3x. So I can go ahead and solve for x now. X is equal to 1/3 of u minus v. Perfect. And if I take this x and I go ahead and plug it back in for x here, I can find that y is equal to 1/3 2u plus v. So now that I have x and y in terms of u and v, we can start talking about how this domain changes. So first things first, we're going to plot the region in xy space that's being described. So I go ahead and I look at my bounds. Well, the x goes from 0 to y equals 1 minus x, and then 0 to 1 in the x direction. This is detailing a triangle like this. So here I have y and x, and I have the points 1 and 1 right here. Down here, this edge is y equals 0. This edge here is x is equal to 0. And here we have that y is equal to 1 minus x. So we've got 3 edges this time, and we got to check all of them and how they transform into UV space. So the first thing we do is when x is equal to 0, so we're talking about this left edge here, I can look at what x is equal to. This means that 1/3 u minus v is equal to 0. Or this means that u is equal to v. So this gives us a relationship in the UV space for this particular edge. Now, when y is equal to 0, I get that 1/3 of 2u plus v is equal to 0. So I can go ahead and solve for this. This means that v is equal to negative 2u. So that gives me a relationship for this edge here, y is equal to 0. Now, when I have that y plus x is equal to 1, I can say that this is 1/3 of u minus v plus 1/3 of 2u plus v is equal to 1. Well, this left-hand side we can reduce a little bit. It ends up that these v's cancel, and all that we're left with is a u. So we know that u is equal to 1. So each edge here becomes a new edge in the UV space. So let's go ahead and draw these relationships. So now this is UV. We have that u is equal to 1. Okay, so let's draw that. Somewhere at u equals 1, we've got this straight line. The other one is v is equal to u. So we can go ahead and draw some straight line. V is equal to u. So it goes out like that, maybe. And then the other one we have is v is equal to negative 2u. So this one comes down at a little bit steeper of an angle. Maybe something like this. Can actually just also extend this down. So this looks like our new region, this triangle. So this is S. Ooh. Here we have that u is equal to 1. Here we had that v was equal to u. And here we had that v was equal to negative 2u. Okay, let's look at our Jacobian. The Jacobian of u and v is equal to our partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. Well, our partial x, partial u was 1/3. Our partial x, partial v was negative 1/3. Partial y, partial u was 2/3. And then partial y, partial v was 1/3. So this becomes 1/3. we get an 1/9 here, and then we add a 2/9, so we get 3/9. So that becomes 1/3. Okay, so let's start setting up our UV integral. So our original integral was 0 to 1, 0 to 1 minus x, the square root of x plus y times the quantity y minus 2x squared dy dx. This becomes, let's set up our double integral. Our integrand, therefore, becomes, the square root was just related to our u, right? So we get a square root of u. And then we get here, this is just v, so v squared. We have our Jacobian here. So we need to take the absolute value of 1/3. Luckily, that's just still 1/3. And now we have to figure out what order of integration we're going to do. So I take a look at my region here in UV space, and I think I would like to do vertical traces like this and just move across. So I end up with a dv du. And that means my v integral goes from the bottom curve, which we said was -2u, up to the upper part of that triangle, which was just u. Dx, therefore, goes from 0 to 1. Okay, so now we can actually go ahead and integrate this. This is equal to the integral from 0 to 1. Then we'll have the square root of u. This becomes v cubed over 3, and then we have a third here. So what I'm going to do is write this as v cubed over 9. And this is evaluated at v equals -2u, and v is equal to u, du. This becomes the integral from 0 to 1, 1/9 square root of u times u cubed plus 8u cubed. Du. So we get a 9 from here. This is 9u cubed. We have a 9th out here. Those end up canceling. So we have the integral from 0 to 1 of u to the 7/2 power, right? Because we get a cubed here, and then we get a 1/2 power here. So we can write this as 2/9 u to the 9/2 evaluated at u equals 0 and u equals 1, which just gives us 2/9. So this way might be a little bit easier for some of you. The difference is we go ahead and we find what x and y are in terms of u first, and then we can just sub in or kind of solve for what these equations represent. So we solve for x and y in terms of u and v, and then we said, okay, x is equal to 0. Well, this meant that if we plugged in the values for x, we had some relationship u equals v. For the y equals 0, we went ahead and plugged in those relationships, and we found that v was equal to -2u. And then for this relationship, the y equals 1 minus x, we went ahead and plugged in those definitions, and we found that u is equal to 1. So once we have how each of these edges transforms, we then plot those edges in the UV space, and you can kind of see the enclosed region now is the thing that we need to be concerned about. Then we just go ahead and take the Jacobian, and we can transform our integral from there. So that way, I think is more common because you don't really have to worry about the ranges all too much. Okay, so now let's talk about triple integrals. I'm not going to bore you with the proof, but remember we had to find the area of those parallelograms. Well, now when we're talking about R3, the volume of that thing was the scalar triple product, which means that our Jacobian, that might be a function of u, v, and w, is the determinant xu, xv, xw, yu, yv, yw, and zu, zv, zw. On the exam, will we always be giving u and v transforms in terms of x and y? Do you mean that I will give you that u is equal to a function of x and y, or are you asking that I'm always going to give you a transform period? Either of those, I guess, is false. I don't necessarily need to tell you what the transform is going to be. Maybe I suggest what it might look like. I believe there's a homework problem that kind of touches on this. And maybe I give you u and v in terms of x and y, and maybe I give you x and y in terms of u and v. So you might have to solve for it. Yeah. Okay, so if this is our Jacobian in R3, so what we can do is now rewrite our triple integral of some function of x, y, and z dv as the triple integral over some new volume S of x as a function of u, v, w, y as a function of u, v, w, z as a function of u, v, w, and then we have the absolute value over Jacobian. This is still dv, but now this is in u, v, w space. So in no particular order, this is u, dv, dw. Okay, maybe you should get some practice with Jacobians. So if you would like, verify that the extra terms in the cylindrical and spherical are what you get from your Jacobians. So go ahead and look at those transforms and see if you can reproduce the extra terms that we've been putting into our integrals. Okay, so let's do another example. So this time we're going to look at the triple integral 0 to 3, 0 to 4, and y over 2 to y over 2 plus 1 of the quantity 2x minus y over 2 plus z over 3 dx, dy, dz. And we are going to have the transform that u is equal to 2x minus y over 2. V is y over 2. And w is z over 3. So this should look pretty similar, right? This is very close to the first example we did. There's just a little bit of difference with the integrand, as well as it's now inside of a triple integral. But the xy bounds are the same. So we can easily verify that we're looking at pretty much the same object. Let's do looking at this guy. So here we have that y is equal to 0. Here we have that y was equal to 2x minus 2. We also have that y is equal to 2x. And then we have that y is equal to 4. So that's what this thing looks like in the xy plane. And now we know that this object gets extended from z equals 1, or sorry, z equals 0 to z equals 3. So there's a few edges that we need to talk about. It's all 4 of these guys. We have that y is equal to 2x. We also have that y is equal to 2x minus 2. We have that y is equal to 0. We have that y is equal to 4. We also have that z is equal to 0. And we have that z is equal to 3. So we need to solve for this y, x, and z as functions of u and v. Well, we've done pretty much just that for y and z before. So we can say that y is equal to 2v from the first, or that one equation. And then we can plug that in and say that u is equal to 1/2 to x minus 2v, which meant that we got that x was equal to u plus v. And then from that last equation, we can get that z is equal to 3w. Okay, so now let's check each of these edges. We're going to do the other variant. So when I have that y is equal to 2x, I get that 2v is equal to 2 times u plus v. This ends up giving me the relation that u is equal to 0. When y is 2x minus 2, this is 2v is equal to 2u plus v minus 2. This gives me that u is equal to 1. From here, y equals 0. This is just 2v is equal to 0, which means that v is equal to 0. When y is equal to 4, I get 2v is equal to 4, or that v is equal to 2. When z is equal to 0, I get 3w is equal to 0, or w is equal to 0. And then finally, when I have z is equal to 3, I have 3w is equal to 3, which means w is equal to 1. So look at all of these bounds. These bounds just describe a cube. We don't even really have to worry about plotting it. We know that S is the set of all points u, v, and w such that u is bounded between 0 and 1. V is bounded between 0 and 2. And w is bounded between 0 and 1. That's pretty easy to integrate. So now let's look at our Jacobian. Partial x, partial u just gives us a 1. Then we get a 1 here. We get a 0 here. A 0, 2, 0, 0, 0, 3. Once we do this determinant out, we end up, this is just a 6. Remember, we still have to take the absolute value, but it's positive already. So the integral then becomes 0 to 1, 0 to 2, 0 to 1, the absolute value of our Jacobian, times our new integrand when we do our substitution. So this ends up being a u plus w, du, dv, dw. This is pretty easy to integrate. I'm not really going to bore you with just doing this triple integral out. This ends up being a 12 if you want to practice. And that's it for chapter 12. So the whole premise of this transform is, find your x, y, and z in terms of u, v, or maybe w if you're in higher dimensions. Find how your region R translates to some region S by each edge from R to S. Then look at the bounds. Form your Jacobian, and then you can actually compute your integral. So again, I want to stress that the bounds aren't directly translated. So you don't take these bounds and plug in these guys here and get the bounds. So notice that for this, if I plugged in the bounds, we had that v was equal to y over 2. This would be v to v plus 1. Well, we just saw that this was a cube. So it doesn't make sense if this was a v to a v plus 1. It's not a direct substitution of the transform here. So please remember that for tomorrow. Okay, looks like Heather and Teddy are here. So why don't we start our 5-minute break, and then you can start your recitation.